Recording in progress. All right, everybody, welcome to our first discussion on materials. All right, so your project 5 that you guys turned in last night now becomes project 6. All right, project 6 takes 2 lectures and 2 labs. Don't underestimate the amount of time that these materials take, please. It's not something where you can just blow it off to the last minute. All right, so today we are going to be dealing with reflections, specularity, and roughness. Okay, so spec, roughness, and basically we're also going to be making metal today. We're going to give that a shot. We might have that carry over a bit into the next lecture. The second lecture is mostly transmission, transparency, refraction. Oops, can't spell. Undo, undo, undo. There we go. Pair and C, refraction, and basically glass. So we will get to metal today. Like I said, that might carry over because it is a little on the complicated side. Each renderer has its own way of doing materials. Arnold, it's, in my mind, it's just a little more complicated than what we used to have in RenderMan. But it's not unbearable. Once you get used to it, you can kind of go, oh, okay, this is what I have to do. So we're going to spend a lot of time describing how to get objects to look like plastic or metal or glass or wood or concrete or bread or, pretty much wood surfaces that we would normally see every day. People do spend their entire careers working on materials. People write shaders, especially the big thing is writing shaders or materials in Substance. There's Substance Designer, and also in Unreal. Unreal has an incredibly diverse and huge library of things that you can do to an object. They have a lot of things that can be coded, a lot of things that you can turn off and on for the user. So there's a lot of options. We're going to basically deal with the basics that as an artist, you should know. Oh, that's got specular, that's smooth, that's rough, doesn't have much specular. It's kind of got its weight knocked down a little bit, or maybe the index of refraction is a little bit different. All right, those are the kind of things we're after, because as an artist, you need to be able to look at something and kind of identify what you're seeing. Whether you're drawing with paper, pencil, canvas, or you're doing it in CG, it doesn't really matter. So today we've got Lecture 6 demo files for you guys, Arnold version. It's basically our playground to try out some of these materials and try to get different looks. I've also got some reference for the bread, for the exterior, and we've also got a thermos or a thermal container that's basically brushed metal for the interior. And we will be using, like I said, the day and night scenes from Project 5 that you already have lit. Good news is we will not be using your comp from Project 5, just the day and the night scenes. Now, if anybody has any questions, please let me know. That way we can stop, we can address them. All right. So just a reminder, have office hours next week on Tuesdays and Thursdays from 10 to 4. Frank will be doing the Zoom Open Lab on Thursdays from 1 to 5. And as I mentioned, like on that first page, we're going to be dealing with reflections, specularity, roughness, and also metal. Hopefully we'll get through that okay. And something called anisotropy, which basically, to simplify it, is basically brushed metal. Or a brushed, intentionally roughened surface. Could be glass also. We're going to be dealing with something called BRDF, which is bidirectional reflectance distribution function. Just say BRDF. It's how we look at objects in two viewing angles. How we see based on two viewing angles. Okay, those viewing angles are 0 degree and 90 degrees. All right, so if I have a sphere here, okay, and I kind of got a camera down here. There's my camera. Okay, my camera is looking at my objects. Okay, so let's give this a different color. So my camera is looking at the objects this way. Okay, so this would be the camera view looking at something directly would be the 0 degree. And our glancing or grazing angle that we see, wait, I'm not happy with those arrows, sorry. Also not happy with the camera. Yes, I know, OCD kicking in, sorry. Let's go back a little bit. Let's make this a little further back. There we go. So we'll call that part of our camera here. All right, so back to this. That's our 0 degree. This is our 90 degree. Okay, so this is called a grazing or glancing angle. Meaning we're not looking at it straight on. This one we are. Straight on. So when we look at objects and we see different levels of reflectivity at these two angles, if we can create that in CG, that gives us much more believable materials. All right, so the whole idea of doing this is because we see different reflectivity at 0 and 90 degree viewing angles. Reflectivity, specularity, however you want to look at it. we tend to see a lot more reflectivity at a 90-degree angle than we do at a 0 degree. If we're seeing a lot at 0 degree and a lot at 90 degrees, we're probably looking at something like a mirror or chrome, something highly reflective. But on most average normal materials, we do not see a lot of reflectivity at 0. We see more reflectivity at 90 degrees. All right, questions so far? Anybody? Does that make sense? Brianna's good. Clifton's good. Thank you. Chanel, Darian, Frenzy, Joni, Kentavious, Marie, Nathaniel, Spencer. Questions? Chanel's good. Frenzy's good. Nathaniel, Kentavious, Marie, Spencer. Okay. All right. So in addition to having materials assignment due, we've also got a materials discussion and a research discussion. Now, the reason I'm mentioning the research discussion is because I want to give you some extra time to research a topic that interests you. The whole idea of this is for you to research a topic that what is your passion? What drives you? Why did you come to Full Sail? So there are some approved research avenues or areas you can go down. One is utilizing the library research database in our library on one.fullsail.edu. Basically connect. Let's go to departments, go to library. All right. EBSCO is a nationwide network of, basically, it's a network of universities that share research resources. So everybody contributes and everybody has access. So there is a ton of stuff out there. Most universities, most colleges, use this EBSCO network. Now, you're not just limited to EBSCO, but EBSCO does have a lot of stuff on there. I do have 2 other online journals that you can use as resources that are not represented in EBSCO. And basically, we've got Game Sutra or Game Studies. It's an international journal of computer game research. Game Sutra, anybody ever heard of that? All right. Basically the art and business of making video games. So they have a ton of stuff there. You can research articles, you can join. They have different areas of interest: programming, art, audio, design, production. A lot of times what they will do is they will feature an article after a game comes out. And basically the developers and the artists and the production people get together and do kind of a lessons learned session. It's basically, okay, this is what we did. This is how things went. If we were going to do it again, this is what we would change. This is what we would do differently. This worked really well. We would definitely do that again. So it's kind of a post-mortem, if you will, or a self-reflection on how things went. Really, really informative. They also have GDC, information there, the Game Developers Conference. Game Studies is a little more formal. They mostly have what are called white papers, which are very, very formal research papers. They have a very specific format. They are presented to a group. That group reviews the articles. It's peer review. So basically when they're doing that research, they're saying, okay, this is what we are researching. These are the tools and the resources that we use to research. And here is an abstract, which is a quick summary of our research, and then they present all their research data. If you go there and get, an article on there, read the article, not the abstract. The abstract is just a couple paragraph summary. You're not really going to get any information out of there. But the whole idea is find something you're interested in. You can go lighting, cinematography, game art, game creation, level design, texturing, rendering, rigging, and animation, you name it, any topic that is related to our industry that drives you and why you're here. So there is a very specific format that you must follow, since this is a more formal discussion than our other topical discussions, right? For this, you must have a citation. Okay, so citation. And we use the APA citation format. All this information is in the 6.3 discussion instructions. All right, so you guys should be familiar with APA, American Psychological Association. It's a very, standard format for here's the article, here are the pages, here's the author, and this is where it's from. It's basically that information. All right, then you must provide the link. If you're using EBSCO, EBSCO provides you with something called a permalink, which allows you to give that to anybody, whether they're logged in through Full Sails Network or EBSCO or not. Right? If you are using Game of Sutra or Game Studies, you can copy the URL in your web browser and use that. That's fine. But if you copy the URL in one of the EBSCO articles and give it to me, when I click on it to go look at the article, it's going to say, this session timed out, or there's an error. It's going to give me an error. Now, after that, you read the article and then you discuss it. Now, the discussion is not giving me a summary of what the article is about. That tells me nothing about how you relate to the article. So everything uses what I like to call the you component. Why did you read the article? Why was it important to you? Why did you think it was motivating? Maybe it wasn't motivating. Why was it not motivating? Why is it relevant to you? How does it fit into what you are interested in and where you want to go? And the whole idea is to share this information with your fellow students. It gives them, and it gives your instructors, a chance to learn a little bit about you, what your passion is, and how you relate to the topic. And you may inspire somebody else to go, you know what, I never thought that would be an interesting topic, but reading your discussion, it's like, wow, I really want to do some research into this because maybe I'm interested in that also. So take your time, find an article that means something to you. Does that make sense? Questions? Anybody? Brianna, no questions. Thank you. Spencer, Nathaniel, Marie, Chanel's good. Spencer's good. Thank you. Frenzy, Kentavious, Joni, questions. Clifton's good. Thank you, Clifton. Darian, Nathaniel's good. Thank you. Marie's good. Okay, so a couple of examples of stuff. If you use EBSCO, you will get kind of like a home page like this, where you've got a citation button, a permalink button, and there will be your PDF article. Now, the permalink button here, when you click on it, it'll come up with a little kind of come up with a little highlighted, not quite window, but it'll sit on top of everything. And you copy that, and that is what you can give somebody. Since you are here in EBSCO already, that will take you right to the article. Citation, you just tell it, click on it, and you tell it what format you want. Like I said, if you're using Game Sutra or Game Studies, you're going to have to manually put in your citation. And a citation is still required. Now, if you forget to give me the permalink, this is something like I'm going to get. Yeah, they change these errors all the time. It says, please log in, right? But I don't want to log in because theoretically I'm already logged in, but that session that you are using in EBSCO is only good for as long as you keep it open. Once you get out of EBSCO, that session information goes away. It's temporary. That's why you need the permalink. So here, permalink worked, EBSCO host, but it only took me to an abstract. There was no link here in this whole area, you know, kind of the top of the, or opening of the white paper, right? There was no information about the full article. We need the full article. Here, we've got a citation, got a link, permalink, in this case, took me to a PDF of a magazine, perfectly acceptable, and then the discussion. So this will be due along with Project 6 and the discussion on Tuesday, April 20th, but start researching now for an article. Okay, if you find something that is not in a listed source here, you think it's good enough, send it to your instructor, either to me if you're campus, you know, I have one of the online sections, or to Anthony Bagsby, he's our associate course director. Send it to your instructor, ask them, hey, I want to use this as my article, can I use it? We'll give it thumbs up, thumbs down. The only reason we might give it thumbs down is it's not a reputable article, it's just a blog, somebody's opinion. We're looking for a discussion on a topic that has credible research and credible information in it, not just somebody's opinion. All right, so any questions about the research discussion, let me know. We're going to head on now and start to talk about materials. So we talked about this type of material when we talked about lighting in lecture 2. Does anybody remember what kind of reflection this is? So why it gets its name is also based on this little visual to the right of how light interacts with the surface when it hits it. Anybody? Well, key light, we're looking for the surface property, Clifton. We're not looking for light. The reflection is a result of light hitting a surface and something happening on that surface. So key light would be your main light source providing main shadow in a composition. Right now, we're just looking at material properties. So we're looking at the reflection that's caused when light hits this surface. Well, Lambert is sort of correct. Lambert is the computer scientist who wrote the code to describe this reflection. So Lambert is only really good in Maya. Now, granted, yeah, Unreal understands it, Unity understands it. A lot of renderers will kind of go, okay, I know it's a Maya material. We'll deal with it. It's not going to be great results because, quite frankly, each renderer has its own set of materials and their own way of describing things, light, shadow, the way materials behave. So Lambert wrote the code to describe this reflection. This is called a diffuse reflection. Consequently, we get diffused light. Off the surface. Why is that important? Well, when we have more organized light, let's take a look at this. We have light coming in, hits a smooth surface, for example, bounces off, we get more organized information. So what do we get? Well, we have the ability to see image, parts of the surrounding. It's basically what is in our environment reflected off of that object. We also have the ability to see what's called a glossy specular highlight. This is a result of a direct light source hitting the surface, bouncing off the surface and into the camera or into your eye. That's why we see these highlights. That's where light finds our eye directly. So, diffused, we have microscopic irregularities. Light comes in, it may come in organized, but it hits this surface, and then little nooks and crannies are going to send those reflected light rays in all different directions, diffusing the reflection off of it. So it spreads the light across the surface evenly. We don't see any organized environment reflections or direct light highlights. Does this make sense? Because this is really the foundation for everything we've been doing so far. We've been doing nothing but, rendering and lighting using diffused materials. The diffuse material in Arnold. We used to do the same thing with RenderMan, the same thing with Mental Ray, done the same thing in V-Ray. It's all the same thing. This way we are not, distracted by shiny or color. Those are the two things that make us go, ooh, that and animation, movement. All right, so when we have organized light rays, like I said, we have the light ray coming in that is called the angle of incidence. When it hits the surface, if it's smooth, it will bounce back at almost the opposite angle. So if it comes in at 45 here, it may bounce back at like negative 45. And this, in the surface, in the middle here, this would be 0. And that is our surface normal. You guys know about surface normals from modeling, correct? All right, so let's take just a really quick second to take a look at how Maya displays these surface normals and how they are kind of calculated. This will just give you a little more understanding as to what's going on. All right, so let's let RenderMan and then Arnold start up. Go, 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 go. Commercial license, non-commercial expired. So that means I eventually have to go back to Pixar and basically take a quick survey, and then they'll give me another non-commercial license, but I'm not using it, so I'm not worried about it. All right, so what I'm going to do is create a simple polysphere. Let's zoom in. Let's kind of look at it from the top here. Actually, let's look at it down here, right about here. That looks pretty good to me. Let's go into 4-view. Let's go to top. And let's show all the cameras. Let's unhide them. Shift H. So here is my perspective. All right, here's my surface. So if I want to display my surface normals, well, first let's assign a Arnold standard surface to it. And don't forget, Arnold standard surface, we're going to at least make the value at 0.18 or 0.5, depending on what our needs are. We use 0.18 when we're dealing with a lot of light, and that'll work. So let me kind of move this in a little bit. There we go. All right, so now I'm going to turn on surface normals, going to display polygon face normals. Okay, so there are my little face normals. If I go back to perspective, there they are. All right, now I want to get back, undo view change. There we go. Let's go back into top. Oh, come on. All right, let's do this. There we go. Okay. So surface normals. Okay, we measure lots of things based on these surface normals. All right, so surface normals give us the ability to figure out where things are in 3D space that are impacting either our light, our surface, or our camera. All right, so the camera is looking straight on, right? So each one of these little surface normals is reporting back to the camera or the renderer where the camera is looking and where the different parts of the surface are in 3D space. So this is how BRDF figures out how to display reflectivity. So here, looking straight on, right, this is going to be 0 degree. Over here, this is going to be 90 degree. So what it means for us is we can have our viewing angle change based on where this surface normal is in space. So the material does that automatically. Okay, we'll see more reflectivity here generally on an average ordinary surface. And usually less than, I should say, less reflectivity than the 90 degree viewing angle. Less reflectivity. So all based on that viewing angle. That also gives us the ability to calculate where light's coming in. So we create a light, create an Arnold light here, right? So let's rotate that around. So now my light is facing the surface. My light hits the surface. The normal that the light hits says, hey, you know what? You are probably about, so this is 0, this is 90, this is probably about 125, 130 degree viewing angle. So everything that we get information on is based off of the camera, the object, the light, and where the light hits that surface normal in relation to the camera, or where that particle effect hits that surface normal, or where that fluid effect or any kind of other dynamic effect can happen. So surface normals are really good for reporting all kinds of information for us. Does that kind of make sense? So surface normals, not just for modeling and going, hey, my normals are flipped, it doesn't display right. Well, the reason it doesn't display right is because they're facing the wrong direction. If they're facing the wrong direction, it can't provide information to the renderer or the light or the camera. All right, so just a real super quick tutorial on this. By no means is that, a complete explanation of everything going on. Just trying to break it down into digestive chunks for you. So angle of incidence, angle of reflection, we got a surface normal here. So having that smooth surface, as I mentioned, also gives us the ability for direct light highlights. Direct light source. That's where we've either got the sun or we've got a lamp on or a flashlight. It hits that surface, it hits the surface normals, it bounces around, but a few of those rays hit exactly where the camera or our eyes are looking. They bounce off there, come into our eyes, and that's why we see a highlight. That's basically light finding the camera or our eyes. So an ordinary average reflective surface is a result of 3 distinct components. One is the base or the diffuse. This is your base visibility. A lot of times it contains the color. In this example, red. Okay, we add in actual reflections. These are environment reflections, things that are in our dome light, that are in the real world. You look at a reflective object, you look at your phone, you take a look at your environment and you go, oh, okay. Wow. All right, going to temporarily turn off my virtual background. And you have to forgive how my room looks. It's basically just a disaster. But you can see the reflections of my environment in my phone. Even the back. Still pretty reflective, right? Got my pen. Now it's got different levels of reflectivity. Got my kind of pen holder. You can see some, definitely a lot blurrier looking than these reflections. Okay, that means this surface is rougher. All has to do with how that surface looks when light hits it. So we have the base, we have actual reflections, direct light, specular highlights, all three together. Remember, everything is additive. All three together give us our final surface. Gives us base color, environmental reflections, and direct light highlights. Most surfaces have a little bit of reflectivity in it. Although things like carpet, very rough fabric. So for example, this little case where I keep my earbuds in, right? This is really rough, kind of neoprene fabric. Same thing that many of you may have as a cover for your Mac. You know, those little sleeves you kind of put it in, right? All the fibers on the surface are basically scattering light all across it. So we don't really have a 0-degree reflection or even a 90-degree. Everything is diffused pretty evenly. Now, this ordinary average reflection is called an isotropic reflection. So ordinary reflection is called an isotropic reflection. Isotropic simply means, and I should have shown this while I had my, oops, sorry about that. There we go. Meant to turn off my virtual background. There we go. All right, so let me see if I can, well, first off, let's, all right, so here, got my light on my phone. My light is hitting, well, it's kind of hard for you to see that. There we go. So you should be able to see the light hitting. Well, that's not an example like I wanted. Okay, how about this? A little close, trying to get a little bit of a light there. All right. One more object. Let's see if we can get this to work. All right, so this is clear liquid, but you should be able to see the highlight on the top of it. There it is, right there. As I turn it around, it's still kind of round. I mean, it's distorting a little bit based on the shape of the bottle. The point I'm trying to get is that an isotropic reflection will display the same no matter what angle the surface is moved at, whether you rotate it or not. So if I rotate this sphere, that round highlight will be the same no matter whether the sphere is upright or upside down. That's isotropic. Reflection, highlight look the same at any angle. Anisotropic, which we're going to get to in a little bit, changes how it looks based on the rotation of the surface. And we'll get to that in a second. But ordinary, average, isotropic reflection. That's what most of the objects that we encounter in the real world. All right, so while we're talking about this, we're going to talk about color. So went to an Unreal, they called it Unreal Fest, was mid last year. They're having another one coming up soon, usually about April. They have them, and basically they get together virtually, and they talk about all the stuff in Unreal. It's Epic who runs it. And the one discussion we were at, they were talking about PBR materials, which are physically based rendering materials. Okay, and their main, well, they were talking about a lot of different parts of the materials, basically stating the same thing. PBR materials utilize BRDF, you know, facing reflectivity is different than a 90-degree angle reflectivity, called a Fresnel reflection, how things look different at different angles. All right, so they were also talking about color. And they say one of the common errors that people make with color is when they see black, they think pure black. When they think white, they see pure white. They said nothing looks worse than having something be pure white or pure black. It just screams perfection in CG. So what they did was they took some pictures of really dark objects and really light objects. For example, they used charcoal, they used snow. They took those photos into Photoshop, and they found that when they sampled the value of the really dark surface, for example, charcoal, it was not a value of 0. So anyway, 0 equals black and 1 equals white. Okay, they found that that really dark black charcoal was 0.02, not completely 0. And then they took some pictures of snow during the day around noontime, and they had pretty good images. They weren't compressed JPEGs that have information thrown out. And they found that the really white areas were not pure white or 1. They were like 0.8. They said maybe up to like 0.9 at the most, but 0.8 makes a really believable looking white. So the idea is white, this is the brightest part of the image. And this is dark, black, darkest part of image. So if you can keep your darkest areas around here and your lightest areas around here, you will get a much more believable looking, realistic render, scene. And they're talking about doing it in real time in Unreal. So I just wanted to give you this information because this is really important when we're adding color into our scene. Especially, we're going to be adding it through materials. So if you see something that's black, don't assume it is completely 0. You see white, don't make it 1. Take your image into Photoshop and sample it if you need to. Back it off so it's not pure 1. Raise it up so it's not pure 0. Does that make sense? No pure black, no pure white. Brianna, Chanel, Clifton, Darian, Frenzy, Joni, Kentavious, Marie, Nathaniel, Spencer, any questions so far? Okay, everybody's good so far. No questions. This is only going to make your art better also. If you're painting, if you're doing, pencil, you're doing watercolor, you basically try to avoid all these absolutes. All right, good. If you do, make sure you ask. All right, so I have a couple of, and I didn't bring my mouse today. Anyway, I do have pictures of my mouse. So this is at my desk at Full Sail. Got an overhead rectangular light. You can see behind the mouse, and basically what you're seeing the mouse sit on is this upside down, pen holder for my tablet. So mouse sitting there, I have a black, basically it's basically a ball cap. That fabric is black, but you can see that black is a lot different than the black here and here and here. So this is a diffuse surface. Just to give you guys an idea of what a diffuse surface looks like. Diffuse surface. This is plastic. And if you wait 1 second, I'm actually going to go get the mouse. I will be right back. All right, back. So here is my mouse, which, all right, I'll just angle it so I don't have to turn it off. So you get the idea. Plastic, see if I can make it come in a little more. There we go. So plastic, pretty reflective. Oh, rats. Turn that off. There we go. So really, really reflective. All right, so I like to use my mouse as just a way to show reflectivity because you can see I've got my window right about here. And you can see outside pretty good. You can see how I rotate it. That reflection is more or less the same. So isotropic reflection on my plastic. All right, same environment, same reflection, but take a look at what happens when it hits a rougher surface here. And take a look at what happens when it hits that rubber grip on the side. Okay, it is really, really rough. That rubber grip is meant to be non-slip. But you can see how much rougher that surface is and what it does to the reflection. It's basically breaking up that reflective information. This one, not broken up so much. And this one, is basically not perfectly smooth, but really, really close to being smooth. So that's what we're actually looking at here. Let me go back, get rid of my ugly room background. So this would be considered a low roughness, highly reflective surface. Sometimes you will see glossiness used to describe it. This would be considered to be a high glossy, low roughness, sharp detailed reflective surface. Okay, so we're going to look at the top, same top that I just showed you, right? This one is medium to high roughness. The surface itself may feel sort of smooth, but it, has some roughness either under the coating or it's so microscopic, it doesn't feel rough to our fingers, but to all the light, it definitely bounces in more different directions than it did with this smoother surface. So, rougher surface, this would be considered a low surface glossiness. Low glossiness means medium to high roughness. Soft highlights, blurry, if you want to try and describe it. Now, same light, same everything hitting the side of that rubber grip on my mouse, right? So this is very blurry reflections. This would be considered a very high roughness surface. Not as rough as my diffuse surface. My diffuse surface is just, scattering light evenly in all directions. There's still a little bit of organization in the light pattern. So this is no longer plastic. This is now rubber. So what we're talking about here is helping us to describe what we see. So you say to yourself, oh, we made that diffuse material, we're never going to use it. Not true. You may use it for things like fabric or really rough concrete or really rough carpet. Carpet, a lot of times, even if it's, not considered deep pile, it's got very, very shallow nap to it. It still has fibers that diffuse the light. So diffuse surface, this one is a rubbery surface. That's what gives us that clue. Rubber. It's going to be pretty rough. Unless, like the sidewalls of a car tire. You get them brand new, they usually put on that stuff to make them look all nice and shiny, right? And as soon as that wears off, your tires look like this. You scrape the curb a few times, it looks worse. All right, so this would be a very low glossy surface, high roughness. Does that make sense? Any questions so far? All right, so when you look at a surface, you need to ask yourself 3 things. And I'm going to call it when looking at reference, because right now we're using reference and you guys are going to get reference for your project 6. This is where you have some creative freedom. We're not providing you with, hey, here's your sofa in the interior. This is what we want you to do. No, you're going to find out what kind of sofa you want to make. Some of them may have more reflectivity than others. Some may be shiny. They may have plasticky or, very smooth leather, or they may have rough fabric. When looking at reference, you ask yourself 3 main questions. One, how reflective is it? This could go for any surface. That ball cap, how reflective? Well, not very reflective at all. Okay, it's not completely a black hole. I'm seeing, a little bit of stuff there. All right, so not very reflective. How rough? Okay, it's rough. It's fabric. And then number 3, what color? Your reference should answer all 3 of these questions. So we're looking at this at a 0-degree viewing angle, right? Here on the sides, there's our 90-degree here. Here's our 0-degree here. It's a little bit more reflective. It's kind of like the direct light hitting it, but without direct light. All right, does that make sense? 3 questions. How reflective is it? How rough is it? What color is it? We're worried about color last. We don't want to be, color is the easiest thing to put on there. What you're interested in is getting the other properties first. All right, so if I go back here, right, 0-degree, and we still have 90-degree here, but I'm going to put my 90-degree up here, right there. Because you can see a little bit of highlight here on the side. Right now, these little edges here are picking up the light because that's where the 2 parts of the mouse intersect. There we go. Well, I don't know. Can I get, yeah, there we are. So right here, there are 2 different surfaces. All right, same thing here. Right, 0 degree, we're looking at here. So we got our 90 degree, or sorry, our 0 degree here, 0 degree, and off here to the side, like here, we got 90 degree. Right here, it's going to be a lot more reflective on those edges up top there. We're not quite getting a real 90 degree. It's kind of hemispherical. So we're getting maybe 30 degrees of a full 90 degrees, maybe 45-ish. Yeah, not even 45. All right, questions so far. That makes sense. 3 questions. How reflective is it? How rough is it? What color is it? If you can answer those 3, you're on your way to describing your materials with some degree of accuracy. Now, when we get into glass on Monday, we're going to talk about, okay, how transparent is it? And does light bend as it goes through it? Some surfaces, like air, and believe it or not, air is considered a surface. It's a medium. It's a gas that we kind of swim around in. It's all over. That's fairly neutral. All right, so when we are dealing with advanced materials, PBR materials, the Arnold standard, the RenderMan Pixar surface, the V-Ray standard surface, okay, they are all going to try to be what we call physically accurate and use conservation of energy, which means you can only have 100% of the energy in a material at one time. And that energy split up between the base or diffuse, the reflection or the spec, and also the refraction or the transmission. This takes care of transparency, glass, refraction. So right now, here, we don't have any transparency. We don't have any refraction. So this would be 0. So most of our energy is being distributed between the base and the spec. And it looks like the spec is much higher here. Whereas when we get to less reflectivity, more roughness, we're getting a little more diffuse and not as much spec. We get here, we're getting a lot more diffuse and less specular. So we're kind of stealing energy from one area and giving it to another. Until now, all the energy that we dealt with was in the base, right? Now we're going to add some specular. So we're stealing from the base and adding into the specular. If you add more reflectivity, the energy is taken from the diffuse or the base. Now, we break our materials up into 2 categories. One is called dielectric materials. Don't be afraid, it's not really that horrible. The other are called conductor or metal materials. And basically, dielectric materials are everything except metal. Everything but metal. Conductors, these are metal materials. So for all your objects that are not metal, we are going to be utilizing, come on, give me that tool. There we go. We're going to be utilizing base color, specular weight. So base colors here, specular weight, and specular color. When we make metal, we're going to be using the metalness feature. Little silly, but metalness is actually used in substance also. So metalness base color, that's what the metal color looks like when looking at it directly. Specular weight, and then specular color. That's the color of the metal, if there is any. We'll get into color in metal. Now, notice these say color, but let's be very specific. Specular color should be white for all materials except red metal. We only add color in the specular for metals to get the edge the right color. I'll say it again. Specular color always stays white unless it is what we call a red metal. Let me go back and talk about metal. So metal can be broken up into two categories. All right, so one of them is going to be white. Come on, you're supposed to give me the draw tool. Thank you. All right, so white metals, things like steel, aluminum, iron, silver, nickel, titanium-ish. And then we have what are called the red metals. That would be stuff like copper, gold, brass, bronze. Now, why are they called red metals? Well, remember talking about light. We asked the question, this is a diffuse material, but why do we see red? Does anybody remember why we see red here? What's happening? Why is that reflected? Why do we see that? Okay, way back in lecture 2, we determined that out of all our colors, every other color besides red is being absorbed. That is correct, Brianna. Remember, when we're dealing with light, our eyes have RGB, red, green, and blue cones in our eyes that pick up color. When all the cones are stimulated equally, we see white, or we see, maybe a shade of gray, but we mostly see white. When any of the other colors is absent, we get another color. So for example, if green and blue are being absorbed, red is the only thing bouncing back, we see red. Same thing here. White metals are white. Just making this blue. Okay, white metals. We see white. All colors are visible when they bounce back. Okay, in red, mostly red is reflected. Now, granted, there's probably going to be a little bit of green, maybe a little bit of blue in there, because these are not pure red. Copper is kind of orangey, so you're going to see maybe a little bit of green thrown in there. Brass, bronze, you might see a little bit of blue thrown in with the green. Red is still going to be the primary that you see, which is why these are called red metals. Now, if anybody's interested in this, I've actually got a link here to a PDF, why copper is reddish in color. All right, the first page is very simple to read. Come on, don't tell me you got rid of my link on me. Come on, come on. Ah, whew, still available, good. All right, so very simple. It basically tells you the same thing that I just told you. All right. Very, very simple premise. Now, that's why all of our reflections, the reflected specular color needs to be white. We rely on our environment to make different colors appear in our reflection. So I'll say that one more time. Let's go back here. No, here. So we keep our specular color white so that we get an accurate reflection of our environment, unless we're doing red metal. Now, the base color is what we see from the object when we're looking at it directly. So here, we're looking at the face color of mostly really dark. It's highly reflective, but it's pretty dark. Most people would call that black plastic. Come on, where are you? There we go, black plastic. Most people would call that kind of grayish. Most people would call that black rubber. All right, so that's what we see at the 0 degree. Specular weight is the brightness of the specular highlight. For the most part, we keep that at 1, and we allow the roughness to do the job for us. So we have specular color. Like I said, this is our 90-degree angle. And basically color information at 90 degrees, which we want to be white unless it's metal. Does that make sense? Brianna, Chanel, Clifton, Darian, Derek, Frenzy, Joni, Kentavious, Marie, Nathaniel, Spencer, please ask questions. Does that make sense? Okay, good. Thank you. Now, one thing I don't have, oh, come on. There we go. All right. One thing I don't have listed here is this IOR. That's the index of refraction. And I'll show that when we go to demo. Index of refraction. By default, it's 1.5, which equals glass. Now, that's pretty good for most surfaces, but I'm going to show you that's actually a little drop down that will tell you, hey, you want plastic? It's slightly higher index of refraction. You want something else? Oh, it's slightly lower. It'll help you a little bit, but we rely on the weight, the color, and the properties, especially roughness, to determine a lot of our material. This is unique mostly to Arnold, right? Like I said, the default of 1.5 is usually pretty good. Most of the time you can leave it, but I'm going to show you a couple exceptions. But these are the main players right here. All right, so to make metal, we turn metalness all the way up. That makes the object fully specular and have what's called complex Fresnel reflections, meaning the viewing angle will change, or the reflectivity will change based on the viewing angle. Now, when we're making metal, the base color should be white unless you're doing red metals, white or gray. How do you know which? I've got a resource that's going to help us in making metal. Specular weight only controls the amount of edge reflectivity. So most of the time, put it at 1, that's fine. Occasionally, you might want to bring it down a little. Specular color controls the edge color only, very similar to what it does here. We only change that if it's a red metal, copper, brass, bronze, gold. Now, roughness is the same whether you're doing dielectric or conductor materials. That is the amount of roughness, how clear or soft or blurry the reflections are. Like here, pretty clear. So super, super low roughness. Nothing's perfect. Unless you've got a perfect mirror, it should not be, roughness should not be 0. Okay, here, higher roughness. How much? I always start with the default. We get 0.2, which is a moderate amount of roughness from Arnold. You can see here, I got it lowered down to 0.1, but the default is 0.2. 0.2, that might work here. You get here where there's more roughness, that might be like 0.4, 0.5, somewhere around there. You'll see as you increase the amount of roughness, we're going to get a lot more breakup in our reflection. It's going to scatter, diffuse, blur. Now, we talked about isotropic reflections, which are our normal average reflections. What happens when you have intentional roughness, like brushed metal? All right, anisotropy is what happens when you have a surface that changes visibility when you rotate it. I have an object here. Let me go grab it. All right, so I have a little 3D printed case here. Let me turn off my background for a second. None. Do I make this bigger? Does that make that bigger? No, of course not. Okay, so compare these two objects. So my mouse shows an isotropic reflection. I turn it, that reflection stays the same. Can you guys see that? Okay, now I have a little 3D printed case here. Okay, this little case, you know, it's cool. You can open it up and hide stuff in it. But this is built on layers of what's called PLA. Okay, so I have lines going up here that basically build this little plastic case. So those lines act like intentional roughness, like brushed metal. Notice that my highlight, let me see if I can get my phone. All right, so here, there we go. So that you can really see that highlight. Now, let's compare that with a smoother surface like this. I'm trying to aim it so the light goes right into the camera. There it is. There's my light. Okay, so you can see that little round dot there. Okay, so let me keep this. And now you can see as I turn the object, that highlight doesn't stay the same. It changes direction because I've got intentional roughness. That intentional roughness means that my highlight changes as I rotate the surface. So it's no longer uniform, it changes direction. Now, anisotropic usually means that you have a vertical reflection, or the reflection is based off of the roughness. My roughness is horizontal, so my highlight stretches vertically, perpendicular to the surface. It's 90 degrees away. And that's what happens with brushed metal. So, for example, I've got this thermal container here that we have in the inside of the interior seam. And we provide reference for you for it, because that was my thermal container. So I took pictures in my kitchen and big window, and you can see I've got a stretched highlight here. So if I zoom in enough, so we can zoom in a little more, hopefully you can see there are some horizontal scratches, hence the name brushed metal. Okay, they are horizontal, so my highlight stretches vertically. Now, to create that in Arnold, it's actually pretty simple. Under specular, we've got this attribute called anisotropy. By default, it's set at 0, which means you get isotropic reflections, normal, average, ordinary reflective surfaces. Okay, to make something stretch either vertically or horizontally, that's going to be dependent on your reference. So, for example, my thermal reference, I got my window in my kitchen, it stretched vertically. I changed my anisotropy to 0.95. I usually don't like to go to 1. It's usually just a little over the top. But it can go all the way to 1. That will stretch it. Now, I want to rotate it so that it looks accurate. I want to rotate it 90 degrees, and this is where it gets weird. Okay, rotation you would ordinarily think of as 360 degrees, right? 0, you got 90 degrees, 180 would be, upside down, basically, 270, 360. Unfortunately, Arnold goes from 0 to 1. So if you want to rotate a reflection 90 degrees, you rotate it 0.25. All right. So rotation at 0, neutral, 0.25 is equal to 90 degrees. 0.5 would be equal to 180. 0.75 would be 270. And then 1 would basically equal 360 degrees. So it only goes 0 to 1. Most of the time, you're interested in rotating it 90 degrees. Most of the time. Like I said, anisotropic materials based on the roughness, the intentional scratches in the surface, that highlight will be perpendicular to the roughness. Perpendicular meaning 90 degrees. All right, does that make sense? Questions? Pretty good. Okay, if you do, don't feel embarrassed, ask away. So I have 3 renders here. The middle one, 0 degree. I got a lot of roughness in it. The one on the right, I increased the anisotropy. I have 0 degree rotation. It kind of stretches it horizontally automatically. Okay, but I want this to stretch vertically. So keep the anisotropy at 0.95, rotate it 0.25. Now I get a nice 90-degree rotation. So making an anisotropic or brushed metal material is actually fairly simple. It does require you to adjust the roughness in order to get the surface to look correctly. Because, as I showed in the reference image, there we go. Showing in the reference image, I mean, my reflections are really pretty blurry here. So it's going to be, fairly high level of roughness, anisotropy, and then the rotation. And of course, this is metal. So we're going to make it metal. And this is going to be all the way up, and we'll get into that later on. Okay, we talked about all of this before. All right, so some resources for you guys. Standard surface link will take you to Arnold. You can learn about the base, you can learn about the specular, you can learn about the transmission. They have all different examples. And it actually is quite a good reference. So under standard surface, if you go down here, just, go to base, find out what base does. This is where you make metal, right? So they've got examples of metal. I'm going to show you, you can use these. I'm also going to show you how to pull information off of another resource called the refractiveindex.info. So this refractiveindex.info is a good kind of library of different materials. It's kind of based on a mythical place called a library, where you walk into a building, you had shelves of books, the books were categorized, you had topics, you had books, and you had pages inside the book where you could find information, sort of like an old school cookbook. Right? You want to go to your shelf, you want to find, oh, I want to make entrees or I want to make dessert. So you pull that out and you go to your chapters. Okay, dessert. Do I want cake? Do I want pie? Do I want muffins? What do I want? So then you find cake. And then you decide, do I want a white cake? Do I want a marble cake? Do I want a chocolate cake? Do I want a black and white cake? Do I want a red velvet? I mean, just on and on and on. You find the one you want and then you go to the page. So here, right now, main simple inorganic materials, the default book is silver, and this is basically the recipe for silver. Now, this has different data based on the time and, well, actually not the time. Well, time, yes, in the sense of the year of when these were measured. So you can see the initial one they give you is from 1972. We got some 2020, 2016. They're going to have slightly different numbers in them. So you find, a lot of times I will come in and just use the first one, see how I like it. If I don't like it, I will try another one. Now for silver, this is great. You got refractive index, extinction coefficient, but for us in Arnold, we're going to be utilizing this information down here. We'll get to that after break. So just want to kind of plant that as a possibility for now. So refractiveindex.info, good reference. The Arnold standard surface, excellent reference. Okay, couple of things. Now that we are adding in specular, we're going to need, when we do our final render, we're going to need to increase specular also, because we just had to worry about camera AA. This is your global global number of samples. And then remember, it's a square root. So at 3, you're actually getting 9. Down here, diffuse, you're multiplying 9, times 3, it's cubed. So down here, we increased our diffuse, which is indirect light. Right? We usually bump that up, maybe 8. Here, now we're going to have to start adding speculate. So the default of 2, that's preview quality. You want to bump it up. Try 4, try 6, try 8. 8 is going to increase your render time a lot. Go 4 first, take a look at it. If you still see noise in the reflections or in any shiny areas, you got to bump it up. Try 6. Still got it? Try 8. 8 should get rid of it. Just remember, you can have a little tiny bit of noise because you're going to denoise it when you do your final render, just like you've done for all your renders so far. You're going to be doing it in the Arnold render view, in the image tab or imager, and then you're going to use the denoiser imager. All right. So good time to take a break. Any questions? Any questions at all? Come back. We're going to do some demos. Follow along. I've got the Lecture 6 demo files for Arnold. We'll come back. We're going to make we're going to try and make the simple properties of my mouse, right? This really nice, smooth plastic part. We've got the rougher kind of button area, and we got the rougher rubber grip on the side. We'll make, we'll try a couple other materials, and then we'll try our hand at metal. Okay, yep, it is a lot so far. Like I said, we'll get to metal a little bit. We're probably going to pick up and do some more on Monday as well. So that's probably going to bleed over. It may be just me exposing you to metal and then let that digest. And then on Monday, we'll pick up and kind of go through it one more time. Now, today in lab, Frank's going to do a little presentation for you guys on look development, finding reference images, and finding good reference for every object that is visible to the camera. And we'll go over what the requirements are before we demo after break. So this is a good time to take a break. Let's come back at 11. Come back at 11 a.m. That'll give me a chance to render out the first part of lecture and hopefully get it uploaded, and then we can pick up. So I will see you guys in 20 minutes at 11 a.m. We're going to try and start right on time. So please get back, and then we will do as much as we can with materials. All right, so I'm going to stop my video, going to mute myself, and I will see you guys back here in 20 minutes. Don't forget, I do have to end the session to render out lecture.